In the 1920s, physicists needed a mathematical framework to test the radical idea that matter acts like a wave. Erwin Schrödinger provided the tools. To understand the shift, look at this comparison. On the left, classical physics, a simple ball bouncing steadily down a hallway. On the right, the quantum view, a continuous wave trapped and vibrating between two strict physical constraints. Let's build that quantum sandbox. We call it the one-dimensional infinite potential well. We start with a single x-axis, confining a particle of mass m to a length of a. Inside this region, the particle experiences absolutely no forces. Its potential energy, V, is exactly 0. But to keep the particle trapped, we have to build walls. We make these walls completely non-penetrable by setting the potential energy to infinity outside the box. This drives the probability of finding the particle anywhere outside this defined space to absolute 0. The particle is entirely locked inside. Applying these rigid physical constraints is what forces the math to behave in very specific ways. To find the allowed states for our trapped particle, we use the one-dimensional, time-independent Schrödinger wave equation. Solving this second-order differential equation yields a general mathematical solution. The wave function psi of x equals a sine kx plus b cosine kx. We have to apply our physical boundaries to this math. At the left wall, where x equals 0, the wave function must be 0. If we substitute 0 for x, the sine term vanishes, but the cosine of 0 is 1. To keep the equation balanced and satisfy the boundary, the constant b has to be 0. With b gone, we move to the right wall. At x equals a, the wave function must also be 0. Plugging that in leaves us with a much tighter equation. 0 equals a times the sine of ka. This leaves us with a contradiction to resolve. We know the amplitude, a, cannot be 0. Otherwise, the wave function would vanish everywhere, and the particle would simply not exist. To maintain the particle's presence, the sine term itself must be the part that equals 0. By enforcing the impenetrable walls of our physical model, we strip away arbitrary variables and force the continuous wave into a strict algebraic limitation. The sine function only equals 0 when its argument is an integer multiple of pi. Mathematically, this means k times a must equal the integer n times pi. That integer, n, dictates the particle's energy. By definition, the wave number k squared equals 2 times mass times energy over h bar squared. If we equate our two expressions for k and solve for E, we get our final formula. The energy E sub n equals n squared times Planck's constant squared over 8ma squared. Notice the integer n. It can be 1, 2, 3, and so on, but it cannot be 0. If n is 0, the total energy drops to 0, forcing the wave function to 0, which leaves us with a completely empty box. Setting n to 1 gives us the lowest possible energy state, known as 0-point energy. This E1 value is greater than 0, meaning a trapped quantum particle can never be perfectly at rest. Like a vibrating string that must have a curve to exist, a particle inside the box must possess energy to maintain its wave nature. Confining the particle mathematically restricts its available energy. We take a particle that could theoretically possess any energy level and compress it into a strict ladder of discrete, quantized steps. We know the energy states, but we still need the exact wave function. Because the particle exists somewhere inside the boundaries with 100% probability, the area under the squared wave function across the entire box must equal exactly 1. Pause the video and try to use the sine-squared trigonometric identity shown here to calculate this definite integral and solve for the constant a. Let's check the math. Evaluating the limits from 0 to a causes the sine terms to vanish. The integral resolves down, leaving us with an amplitude a equal to the square root of 2 over a. With the constant a determined, we have the fully normalized wave function. This expression allows us to map exactly where the particle is most likely to be found at any point between the walls. This visual shows what that math unlocks. By squaring the normalized wave function, we create a probability density map. These shaded areas show exactly where the particle is most likely to be found for the first 3 energy states. Compare the first 2 states. For n equals 1, probability peaks directly in the center, an antinode. But for the second energy state, the probability at the exact center drops to absolute 0. This is a node, a point where the particle will never be found. Watch what happens as we increase the energy state. The nodes multiply and squeeze closer together. The higher the energy, the more fragmented the probability space becomes. This single model gives us three mathematical tools: the normalized wave function to define the state, the formula for discrete energy levels, and the exact locations of every node. Adding impenetrable walls to a void is the mechanism that limits matter. By giving the particle a strict boundary, we force it to obey the quantized rules of quantum mechanics. In the 1920s,